What's up, my nerds? Today we're talking about op amps. These are some of my favorite circuits to play with in the lab and also to analyze on paper. They're the triangle looking things, and because of that triangle, people, their first time dealing with them, they'll just throw up their hands and say, I have no idea what to do here. I'm going to teach you that they are more simple than they look, and you're going to learn to love them. In talking about op amps and how to analyze them on paper and in schematics, we are going to use the node voltage analysis method, or in other words, employing a lot of KCL's, Kirchhoff's current law. So if you haven't yet really nailed down this method, you might want to go to my other video that talks about the node voltage method in detail. In this video, we won't talk about how to use this method, but we are going to use it frequently. All right. Whenever you're analyzing a circuit with an op amp in it, you have to make two main assumptions, and these assumptions you always have to make anytime that you're dealing with an op amp. All right. Otherwise, the analysis would be much more difficult. So this is one of the great things about engineering. It's something that separates us from our brothers over there in the math building, is that we assume things to make our analysis easier, right? And so that's very true when it comes to an op amp circuit. So when you're here's a schematic symbol of an op amp. It's always a triangle, and there's two inputs. There's a negative input and a positive input, and then there's one output over here on the right. Okay, the two main assumptions that you need to make, and you should memorize these. The first one is that the op amp itself, with its two inputs, has infinite input impedance, meaning that current does not flow into the op amp, right? So I guess to denote that, here you have the negative input. I'm going to put some hash marks on the negative input and the positive input, meaning that the current does not flow into the op amp. Okay. The second assumption is that there is a virtual short between the inputs, right? So you have your negative input and your positive input, and assumption number two says, go ahead and pretend like there's a piece of copper that's shorting those two inputs on the inside of this op amp. So whatever voltage is on the negative input, that same voltage is going to appear on the positive input, and vice versa. So there's no difference in voltage between those two inputs. If you remember these two assumptions, whenever you're dealing with an op amp, you'll have no problem with analyzing the circuit and finding whatever you need to find. So these are key. You can't forget these. So put these away in your memory banks and write notes and do whatever you need to do to remember that whenever you're dealing with op amps, you have to make these two assumptions. All right, so what is an op amp used for? Well, it stands for operational amplifier, and the quick and dirty of it is it'll take an input voltage and it will amplify that input voltage so that the output is some predetermined multiple of the input, right? When I say predetermined, the gain of an op amp is designed. It's by design, right? And what's cool about the op amp is the gain is controlled by external circuitry. Okay, so here's the op amp itself, and this is what you see here. That triangle, that represents the entire op amp, right? That's an actual device, that like a chip that you would put in your circuit. And then you, as an engineer or designer, you would put resistors or other circuitry surrounding that op amp, and you determine the gain that you want this entire stage to have, so that way when you have an input voltage, you would get a certain multiple of that input voltage on your output over here at V out. So these are extremely useful, and it has a lot of real world applications. Anytime you have a small signal, a small voltage signal, in order for that to be useful, a lot of times you need to amplify it before you send it to an analog to digital converter, for example, right? And then you can, once you go through the ADC, then you can actually do things with that signal and filter it and make decisions. So we use amplifiers in almost everything when it comes to sensing the real world around us and then sending that to the digital arena so that we can do calculations and do cool stuff with it, right? So this is why amplifiers is so fun, because it's our link that we have between the digital world and the real world. It's one of the important links that we need in our circuits, right? Another thing to point out with these op amps is they're not magic, right? So one thing that's not drawn here is that this triangle here, which represents a chip, is actually powered independent of this circuitry that's actually drawn here, right? So if I were to draw, sometimes it looks like this, where sorry, that's a, let me erase that. So maybe this is like negative 12 volts, and right here it's positive 12 volts. So this actual chip has power to it, just the chip, right? And so in this case, it's powered with two sources. It's actually powered with a positive 12 volt source and a negative 12 volt source. So the full range of voltage that this op amp has available for it is a total of 24 volts, right? From negative 12 all the way up to positive 12. And so what that means is whatever voltage this is, VS, let's say VS is 1 volt, right? And let's say our gain of this whole stage, we designed the gain to be 10, right? And so 1 volt would come in. 1 volt would come in from VS, and it would go through this circuit, and by the time it comes out, that 1 volt would look like 10 volts. And in fact, in this case, it would look like negative 10 volts because it's being fed into the negative input. Okay, so this is we would call this an inverting stage. And so we would get negative 10 volts out. Now, is that magic? Did we create that out of nothing? Well, no, because we're powering this chip with positive 12 volts here and negative 12 volts here. So the voltage range is always there, right? Because this chip has that full range available. Okay, and in fact, let's say that this whole stage has a gain of 10, and let's say that VS comes in at 5 volts, right? So 5 volts would come in, and then it would go through the circuit. When it comes out here, it would want to be negative 50 volts, right? Because it's inverting, and so it'd be negative, and then there'd be a gain of 10, and so 10 times 5 is 50. But there's only a full range of 24 volts available. And so what you'd actually see on the output, you would see negative 12 volts. So it would try to get there, but then it would be limited by the amount of voltage that you're actually powering this op amp with. So that's just to give you a little bit of a clue. A lot of people get hung up and they wonder where all this extra voltage is coming from in this gain stage. Well, it's always there, right? And it's just available and waiting to be used. All right, so I redrew the circuit so it's a little bigger so we can start to analyze this. I want to step through with you how to derive all of the memorized gain equations that you're going to see with op amps. I'm a big fan of memorizing, but only it only works when it works, right? That if you rely on memorizing everything and then you happen to have a bad day or you can't remember where the minus sign goes, then everything is just lost. And so especially when it comes to taking tests, it's really useful if you can, yes, go ahead and memorize the gain equations. They're easy enough, but it's really nice if you could do a sanity check and just derive it as well. That way, you're coming at it from attacking from both sides. So here's a typical op amp stage, right? So here's our op amp again, the triangle. There's two inputs. You have a negative input right here and a positive input. Okay, and that should look more like a positive sign with my ugly circuit. Okay, the positive input is connected straight to ground. Okay, the negative input has all this circuitry attached. So you have the V source here coming in through R1, and whatever this voltage is, that's being applied to the negative input. And here's your output, and then there's what we call negative feedback, right? We call this negative feedback because voltage from the output is literally fed back through a resistor to the negative input. Okay, if it were fed back to the positive input, we would call that positive feedback. Typically for a proper gain stage that's stable, you don't want positive feedback, you always want negative feedback. Okay. As a side note, that's how oscillators are made, is with positive feedback, because they're not stable, and so they'll oscillate back and forth, up and down, up and down. So back to this stage. So we would call this an inverting stage, right? Because the source is feeding the inverting or the negative input with negative feedback. Okay, so we're going to go ahead and let's say we completely forgot our memorized gain equation for this, but our task is to find V out, right? Sometimes they'll say, well, go ahead and find V out over Vs. Okay, well, when they say find V out over Vs, you see Vs is the input and Vs is the input, V out is the output. When they say find V out over Vs, they're really saying find the gain, right? The gain of this stage. Because the definition of gain is output over input. Okay. So great. So we're going to go ahead and, like we mentioned before, we're going to use the node voltage method, right? So remember from that video, when we dove into it, we want to identify all the nodes in the circuit, and we want to give those nodes a name. Okay, so let's do that now. So here's a node, that's our ground node. So that already has a name, which is ground, right? And by the way, this is ground over here. So I'm gonna go ahead and just, right by that guy, I'm gonna label that 0 volts, right? Because that's ground, okay? Here's a node, and if this is ground over here on the negative side of the source, this node I know immediately is Vs, right? Because the value of this source is Vs. So there's Vs volts on this wire right here. Okay, there's a resistor. Here's another node right here. And what do we know about this node? Well, when we go back up to our assumptions, assumption number 2 says that we're going to assume there's a virtual short between the inputs. So the negative input voltage is the same as the positive input voltage. So we take that over here and say, okay, what's the positive input voltage? Positive input, its voltage is 0. So immediately we're going to assume, let me get my pen again, we're going to assume that there's 0 volts right here. Okay, great. So basically this node is also ground, right? Or it has the same potential as ground. This is our last node that we haven't talked about yet, and the value of that node is V out, and that's already labeled. All right, so that's step 1 of our node voltage method, right? We've identified all the nodes and we gave the nodes a name, right? Step 2 is identify the junctions where current is changing or potentially changing, right? And we're gonna make a circle around that. So I'm gonna go ahead. Well, it turns out that current actually isn't changing here, but it looks like it might, and so I'm just gonna make a node or a KCL here, Kirchhoff's current law, right? Cool. All right. Once I do that, I'm going to grab my blue for my currents, and I'm going to assume current is leaving that junction. All right. Now, am I going to draw current going into the op amp? The answer is no, because of my number 1 assumption here. I'm assuming that the op amp has infinite input impedance. In other words, no current flows into the inputs of the op amp, right? So right here, I know that there is no current at all, okay? So I'm actually, to remind myself of that, I am going to put hash marks right there so that I don't make any mistakes thinking that there's any current going in there. All right, so I've identified a node and I've identified a KCL that's associated with that node. So I am going to go ahead and continue with my node voltage method, and I'm going to make a KCL equation at that node. So this is, I'm just going to label it, do it in black. This is my KCL at, I'll call this my negative input, right? So what does the KCL tell me? The Kirchhoff's current law? It's the sum of all the currents leaving and entering a junction equals 0, right? So 0 equals this current leaving, so starting here and leaving from right to left is, in terms of Ohm's law, that's 0 minus Vs over R1, right? So I'm putting, just as a reminder, I'm putting currents in terms of voltages and resistances, right? Just like what Ohm's law tells me to do. the current leaving this way is 0 minus V out over R2. So I'm going to add that. 0 minus V out over R2. Okay. And that's it. That's my equation for this KCL right here. If I look up, I want to find V out over Vs. In other words, I want to find the gain of this stage, right? So looking at this single equation that I made, my only variables, assuming R1 and R2 are known, which they usually are, I only have V out and Vs. So I don't need another equation. I'm good with this one that I have right here, because I can now manipulate this equation to get V out over Vs, and we'll see what we get, right? So we'll go ahead and do it with you. So we got, gotta get rid of my, there we go. So we got 0 equals negative Vs over R1 plus negative V out over R2. That translates to V out over R2 equals negative Vs over R1. And then if I scroll down, make more room, I get V out over Vs equals negative R2 over R1. And that is my gain of that stage. So a couple things to note here, right? One, it's a negative value. So I'm saying the gain of this stage, if I start at Vs, then I go to V out, I'm going to get a negative value, right? Well, that's good, because this is indeed an inverting op-amp stage, right? I'm feeding my Vs, my source, into the negative input of this op-amp. So I would hope, this is like a sanity check, I hope that my gain is a negative value. The second thing to note, and this is just cool, is that the gain of this op-amp stage is completely dependent on the resistors that we put around it, right? And so this is a powerful tool. You can give me an op-amp, and I would thank you for your op-amp, and do what you want with it, right? Okay, well I need a gain of 10, and so I'm gonna make R2 a 10 kilo ohm resistor, and I'm gonna make R1 a 1 kilo ohm resistor, and I'm gonna put them in my circuit like this, and boom, I have a gain of negative 10, right? So this is if you like circuits, like playing around with circuits, and that's an exciting thing, because it puts the control in your hands, and you can do fun stuff with it. So this gain equation for an inverting op-amp with negative feedback, this should look familiar to you. So this is something that a lot of people will memorize, and that's okay, but I do recommend you do this practice just in case you forget. Also, the circuit might not look as simple as this, even though it might boil down to a gain equation that's very similar to this. It might not be as simple. So I know when you're doing homework, and especially on tests, I would practice this using the node voltage method to determine what your gain is for your op-amp stages, because then you're not relying on memorization, you're actually finding it every time. So let's look at another stage that I already drew for you. Here's an ugly circuit, and only because I drew it. What you notice differently here is where before we had the source feeding the negative input, now we have the source feeding the positive input. The other circuitry stayed the same, so we still had negative feedback, right? And we still have this resistor here, but now it's tied to ground over here. So again, the question remains, and let's find the gain of this stage, which is V out over Vs. Let's find what V out over Vs is. So a couple things to note. We know that Vs is feeding into the positive input, and so we better hope that our gain is a positive value, right? That's one thing that we'll remember when we're checking ourselves. Okay, so again, this is an equation that you'll probably memorize, well, at least the gain equation. But we're going to practice deriving that equation using the node voltage method. All right, so I'm going to come over here. We're going to start with our two assumptions we always start with, right? So that the first assumption is that virtual, well, I guess not in order, but the virtual short assumption, meaning that we assume that these two inputs are shorted together, meaning that the voltage on the positive input is the same as the voltage on the negative input. So we know just from observation that this piece of copper here has Vs volts on it, right? Because if there's ground right here and you have your source, then this has to be Vs volts, okay? And so because of the virtual short, we know that there's Vs volts right here on the negative input side as well. Awesome. So now we have all of our nodes labeled. This node's labeled. This node is labeled for voltage. This node is labeled because it's ground, and then this node is labeled because it's V out. Okay. So we're ready to draw our circle to do our node voltage methods. We'll draw a circle right there. We'll assume current is going that way, and current is going that way, and this is just to create our equation. And then we know, because of our assumption, that current will not be going into the op amp, right? So I'm just going to put hash marks there so that you don't forget that. All right, so let's do a KCL, Kirchhoff's current law, at the negative input. KCL tells us that the sum of all the currents at a junction equals 0. So we have 0 equals this current. It is Vs minus 0 over R1, right? Because of Ohm's law, minus 0 over R1. And then plus this current, which is Vs minus Vo over R2. Okay, and that's it. So those are the two currents that we drew there. They show up in this equation. Now we want to find V out over Vs. With this one equation, we should be good, right? Because we have Vs and we have V out. We don't have anything else. So we should be able to find V out over Vs. Let me drag it down here. Okay, and then continuing, we'll put V out on one side. We'll put Vs, we'll take Vs out, and R1 plus 1 over R2. Okay, and then we'll keep going, so then V out over Vs, which is what we want, by the way. We want to find that, equals, and then the R2 will come over and multiply. So we'll have R2 over R1 plus 1. All right, and that is our gain equation for this configuration right here. So let's do a sanity check real quick. Will this ever be negative? Well, no, because resistances won't be negative, right? And that's what we expect when we just look at this. We say, oh yeah, V source is feeding the positive input, so we better not get a negative gain equation. There you go. So again, this is another thing that you could potentially memorize. Compare this gain equation to this gain equation that we found earlier. You'll see there's a slight difference, including the negative, but they're pretty similar. But again, my recommendation is I would always find your gain equations by doing the actual analysis, right? It's good practice, and you don't run the risk of misremembering something. As a fun side note, if you want to make a gain stage with a gain of 1, then this would be a good configuration for that, because if you see this equation, we do have a 1 term in there. And so if you can negate this or neglect this R2 over R1, and a good way to do that would be to make R1 relatively large compared to R2, at least 10 times or more compared to R2, then this term is negligible, and then so you basically have a gain of positive 1. Why do you want to do that? A lot of times in design, you'll want a buffer stage, right? And so a buffer stage, a good buffer stage would have a high input impedance to that stage, and it's hard to beat an op amp that's assumed to have an infinite input impedance. And so you could use an op amp, and which gives you a really high input impedance, and then you can configure that whole stage to just have a gain of 1. So all you're getting is that high input impedance, but you're not actually changing the signal because it has a gain of 1, so you're just multiplying it by 1. So with just what we've discussed, that's really what you need to know. That's the nuts and bolts of what you need to know to be able to analyze any circuit with an op amp. The professors and textbooks, they like to get tricky, or try to get tricky by cascading op amps together in certain configurations, and then asking you to find the overall gain of that entire circuit. My suggestion there is just to take it one piece at a time, and if there's multiple sources, then use superposition. Well, that's eliminating one source and then finding the output that's associated with the active source, and then swapping and find the output that's associated with the second source, and then adding the two results together, right? That's superposition. And I can have a video discussing that in more detail. As far as bringing or cascading the op amp stages together, here's some shorthand that might be helpful. So let's say that this is one entire stage. We'll call that stage A, and then here's another entire stage B, and we'll go even more, another entire stage C, right? And here's V out, and here's VS. Okay, so ultimately they want you to find V out over VS, or that, in other words, the gain of this whole thing, right? Well, depending on the configurations, right, because you'll have resistors and everything surrounding all this, it could look overwhelming, but remember to take it one stage at a time. And what I would do is label these middle voltages, right? Which you'll be doing anyway, because you'll be using node voltage analysis. But I'm going to label this V1. I'm going to label this V2. And again, I'm shorthanding this just to get the point across, but when you look at stage A here, the gain of stage A is V1 over Vs, right? And so you're going to do analysis and you're going to find what V1 over Vs is, okay? And remember, ultimately you want V out over Vs. Okay, well, we're not quite there because here we have V1 over Vs. Then you look at the gain of stage B. Well, just looking at this, what does the gain of stage B look like? It'll come out to be V2 over V1, right? V2 over V1. Okay, so just right there, from A to B, it turns out that when you cascade gain stages, their results just multiply, right? And so when you multiply these together, V1 goes away, right? You have V1 on the top over here and V1 on the bottom. And so that gives you V2 over Vs. Well, that's good because we need Vs to survive the whole cascade because it's in the final product that we want. So we have V2 over Vs by the time we get past stage B. When we hit stage C, the gain of stage C is V out over V2, right? Write that here, V out over V2. If you multiply those two together, what do you get? The V2 cancels and you end up with V out over Vs. And that will end up being what you're looking for. The gain of the entire circuit. So I bring this up because this will allow you to just organize your analysis, right? When you see cascaded gain stages, just take it one stage at a time, and then I want you to manipulate the algebra so that you get the output over the input for that stage. So in this case, it was V1 over Vs. And then for the next stage, manipulate that one so that you get output over input, or V2 over V1. Multiply those two results together to cancel out the V1 terms, and then keep doing that, working down the line until you get what you want. All right, that wraps it up for op amps. I hope you fall in love with them as much as I have. They're really not that hard. Don't panic. Just work through it step by step. And if this video is helping you get your homework done and helping you prepare for tests, go ahead and like and subscribe, and I'll keep them coming. Thanks.